Okay, so we're going to start with hash tables. The reason why we're not jumping into graphs is that we're not done yet in exploring the data structures for searching and implementing the maps. Because at one slide that I shared with you, when we were doing the binary search trees, is that we said to implement the map ADT, we tried it with unordered sequence, we tried it with ordered sequence, and then we said, okay, we're going to check binary search tree, ABL, and for trees. But we also mentioned that there is another way called hash tables that also we can implement maps with it. So just to keep the flow of the map, we're going to cover it and then go back to the graphs. Now, hash tables are going to take you out from the idea of trees. Graphs, it's more connected to a tree. Why? Because tree is a specific type of graphs. That's why usually sometimes we cover graphs right after the trees, but still hash table, it's still very beneficial. Now, why we want to keep talking about searching? Maps is what we said the main thing about maps will help us have efficient searching. But because searching is usually one of the most common tasks in operation that you'll find everywhere, so that's why scientists spend so much time trying to make the searching efficient. That's why you will see lots of data structures trying to cover the maps ADT or the searching part, correct? But someone may tell me, may say what? Didn't we prove the best thing that can happen? But we actually proved that instead of linear O of n, we can search by what? O of what? Log n with the trees, correct? So why should we keep talking about this? So let's just give a scenario. So let's assume for some reason you're in a camp or something. Let's try a second. Why is not able to use screen? Second, for some reason, I'm able to use the touch screen. Sure, why? Okay, I'll try to use the mouse. So it is also not very. So let's assume this person here, for some reason, we're in a, I don't know, in a camp or whatever, and you're super bored and you're using your phone, the internet or whatever, and then there's a problem. We need to reset the router. Okay, just inventing a scenario. For some reason, we have a wall, very long wall, that have poles in it, for example. Let's say we have lots of poles. And you want to go, and you know that the router will be at one of these poles because of the electricity. So if I want to search, where's the router? I'm going to make it easier on you, say ordered sequence, non-ordered sequence, we're going to throw it away. Why? I don't want to come here and start from what? From the beginning, it's going to be O of n, worst case anyway, correct? So what is the solution that we said it may save us? Time. Exactly. For example, we're going to say, to be able to make it easier for us to search, what if we just go right away to the middle, okay? And then I'm going to go either this way or this way, correct? Okay, this will save the time, so it's going to be maybe logarithmic. And we thought, we celebrated, we said, okay, this is the best thing that can happen for searching and all these kind of things. But if you want to think about it, let's say you lost your keys at home and you want to search. And you're in the room, this room, and you're going to search for every spot. what if you know exactly in which drawer you have the keys? So you're going to go right away where? To this specific bucket or drawer or whatever. So this is of what? Of constant. We didn't cover any of these scenarios that it may actually take you off constant to find something. Correct? But what if I tell you there is a data structure that will allow you to have off constant to search? Too good to be true. Correct? It's actually too good to be true. But there is a data structure that we're going to talk about today. If it was implemented correctly, we're going to end up with O of 1. How? How can we imagine this? Okay, think about it like this. This is our room. I have these specific seats, and I want to be able to go to you, to reach to you as a student right away without searching for you. How can you sit, or what is the address that I can link to the seats so I'll be able to go right away to you? From what we talked about before, Taha.
Like a key value.
Very good. The first step is that in a MAP ADT, to be able to do these things, I always need, additional to the value or to the data, which is you as a student with all of the information, I need a key to be able. What did we give an example when we were using the 243s and all of these things? What type of key we should use for you as a student? Yeah, so which one is unique data you have, for example? Student ID. So if I want to continue with the process that we've learned, said, okay, I'm going to choose your student ID to be able to give you a specific address because it's unique. I can go right away to you. Now, what's the problem? If I want to implement this in a real life example here, what's the problem? If I want to keep, what is the problem? There is no problem if I want to do log of n. Why? Because we actually learned how to do it log of n. Now, what is the problem with this if I want to keep O of constant? Think about the bit, guys. Let's say what is the problem again. I want to be able to access your data, or access you here in the class to make it just a better example, and O of constant. We said to be able to do that, I need to know your address. Previously, we said to be able to have a unique key as an address, maybe I'll choose the student ID. Because it's unique, then I'll be able to move in the tree. Now, I want to keep the accessing O of 1, O of constant. And I'm using the student ID. What would a problem happen here in this class? Not theoretically, in this class, what will happen? Because I want to create these seats, right? I want to create this class to be able to designate you to your proper seat. Yes.
So I feel like in a class setting, it's not enough that we have one student number. Again, it's like we are stood out from the class. So if you're a student, you have to have more than just the student number.
More information, you mean?
We set randomly, like you don't.
Sorry, Raju.
Randomly, you don't know every time you that.
No, because technically I want to implement something where I'm creating seats for you with your student ID, so I'll be able to go right away. So that's the problem. What would the problem be? Because if I'm doing this, I'll be able to access O of 1, O of constant. But what is the problem with this approach?
We try.
Jaden,
You don't know where to find the drawer?
we're talking about here about the class. About the class. Luke.
Well, we don't know if every student is in this specific point.
No, if I tell you, let's say your student number is 555, I'm telling you this is the 555, so you're going to be able to sit here. So no, think about what would be a problem, Riley.
For one, if every student sits in their specific seat, you couldn't have another student sit in another seat, so no other student could ever use it. Also, you can only make the room so big. Once you've built it, you try to add more students than there are room, then you run into a problem. You have to get another room for something else.
Okay, Andre.
So if you want constant access, you want an array-based implementation. And if you're doing that with the student number as the index, then you have like 300 million empty indexes at the beginning, just wasting memory.
You see, guys, that's how I want you to think. Build on what we've learned so far. We started with something very important, constant access. Right away, for example, Riley linked it. Okay, constant access, that means I need to access by index. That means the best thing is to have an array to be able to access by index. Then he started talking about what is the problem here. Riley, the same thing. He talked about maybe the space and all of these things. We want to take what we've learned so far and try to see how can we improve the skills, how can we choose a good design, what's the problem, dissect the problem. Now, that's very good. One of the most important thing is if I'm creating a class based on the student ID, let's say I have a student ID that can fit 7 digits, okay? If I want to have seats based on these unique student ID, how many seats are to create? 10 million seat. 10 million seat to be able to cover all the things. So let's visualize it. So look here. Look, if I'm creating this array or these seats, and I want to use the 7-digit student ID. I keep incrementing the student ID, I'll end up here with, I will need 10 million to cover all the aspect of these 7-digit. Now, what's the problem with this? I don't have 10 million students now, so I'm wasting lots of time, lots of space. And why I can't just take only your ID? Let's say student number, student ID. Some people dropped. Some people are what? Alumni, they already graduated, but you cannot use their student ID. It's still linked to them. So that's why actually one of the problems is no, it's not going to work to be able to have this. So let's think about it more. Now, what is the solution? Maybe it's in the key that I'm choosing. Maybe the key, the student ID is not a good idea. So what else I can choose? Again, student-wise. Taha.
So like, because we already have some information about our key, our index, it's gonna start from like, you know, like. It's gonna, so what if we can say, like, if there is like a way that we link, our first index, like our number one. To the first student number, like, something like a function or something, you know, like.
But still, if you still want to use the student ID, you need to actually have this much of seats to be able to do the constant time. Unless you need to find a different way. Who can think about it from a different perspective, not from this perspective? Yes.
Maybe we can assign a new key to every existing student number.
Very good. Here we're saying, you know what? Why do we want to use the student ID as a key? Why can't I assign a new key? That means generate a new key for each one of you, specifically for this class. For example, instead of checking your information, okay, you have a unique key, you have a student ID, but you know what? In this class, I'm going to hand you another paper or another whatever key that you're going to use for this. So I gave you, or I generated a new key for you. This will be similar to what, guys? When you go to the undergrad office, do they serve you based on your student ID, or you have to actually book a number now, and then you're going to use this number as your, let's say, your unique key, and they will call this number. That was a priority for you, but you get the idea. So that's a very good. So we're thinking here, maybe we need to generate a new key, but someone else is going to reply, say, you know what, why can't we use the names instead of student ID? Because we have less names, for example. Riley.
Names aren't really unique, but they have this.
Very good.
Likely, but you could have the same exact name.
Exactly. So that's another thing. Now we're linking it back to the main ADT. We said map. If you have a unique, what if you have the same name? That means if I said, okay, this here seat is for someone named Riley, and then we have 3 Rileys. What's going to happen this time? Yeah, catch me outside. Catch me outside. So it's going to actually have a problem. So we cannot use this. Yes, right.
If you were to assign a new key to your old key, you would have to have a list of all the keys and what the keys were for the, that also sounds like another map, but that also has the same problem.
So now here we're touching on one thing. That's why we said hash table are super useful of constant, you know, of constant, like it's super useful. It's not like better than log n, it's of constant, but it's much more complex to design the hash table in the beginning. Okay, so there is always advantages and disadvantages to everything. Okay, so but you get the idea now. That means if I want to have a constant thing, the first thing I want to think about is that constant mean index mean I have to build an array. Okay, if I want to build an array, I cannot now have everything. So a solution will be what? What if I can minimize this 10 million number into 10,000 somehow? I'm going to minimize it till 10,000, and I'm going to say I'm going to generate for you keys. The keys will never be greater than 10,000. And then we're going to fit them here. So we went from 10 million to 10,000 like this, for example. How can we do something like that? One of the things that we're going to see is we're going to use a function to transform this integer to something else. If I have this, if I take this thing and I do modulus 10,000, what do we mean by modulus 10,000? Usually when you use modulus, you cannot exceed this number. So if I say modulus 10,000, that means whatever output from this equation, it will never exceed 10,000. Modulus 200, it will never exceed 200. So this is one of the things that we're going to actually see it. So generating a new key, that's the first thing I want to do. And to be able to generate it, I need to use what? Like a function. Okay, now that means also I'll need to be able to convert everything into numbers or integers to be able to work with them. Okay, now two main things that we talked about: generating a new key, generating addresses, and what else did we say if we have multiple names? Because even with these keys, what if, because think about it, I'm fitting 10 million into 10,000. There is a big chance that we may have what? Duplicates. We're going to call them collisions. So these collisions, we need to be able to solve them. Why? Why can't I? Who can give me an idea? So let's say here, I have this, and then there's a duplicate here, for example, at 2. So what can you do? Something again from what we learned. Think about this thing here is an array, has an index, and your key was generated. It ended up at 2, at 5, at 10, but then James' key also at 2. So what can we do from a memory perspective?
Giving a priority.
For example, giving it priority. Okay. Nested arrays. Yeah, but do we have something called nested array, or we have something that has an array, but
Table, actually.
yeah, no, we don't want table, because table is going to be matrix. You may end up with n square at some point. No. So we want to keep it an array and add something to it. So you're almost there. What did we see any data structure that actually can have an array and something in it and the index? Abed. Positional list, for example, but it's not positional list, it's the sequence. For example, one of the things that we saw is that we can have an actual array, but then here we'll have a pointer to what? To a node. And then this node will have a pointer to a node. That means there is a linked list inside each index. Okay, so we'll have something like this. Okay, at this point here, so this index will have a linked list. So I'll have a node here that will actually point to another node, and then like this, so a linked list. This will solve the issue. What's the problem with this thing?
Well, an infinite amount of people. That same index, now you're not O1 anymore.
I solved the problem of having collisions, but I solved it in a not very practical way. Because now I'm ending up, okay, I reach O of 1 right away here, but then it may end up with O of n if I have humongous amount of data. But even if I'm not ending with O of 1, even if it's only like, for example, 7, I want you to think about it from this way, guys. Unfortunately, the writing thing is not working, so I'm struggling to show you things, but bear with me and let me try with the mountain. Shoot, there you go. Okay. So I have this array. And I have, for example, value here. Name starts with A, another name starts with B here, whatever, something here. See, all of these are values, okay? And then the now, if I just want to store stuff here, that's my nodes. I have two choices, for example, either store something like this as a linked list. So if I want to get access to this one here, what's going to happen? I'm going to go to this, this, and then this, okay? Correct? So it'll take me 3 times. But then if I want to just go here, so it's going to take me 1, 2, 3, and there is a 4th one. So this one here, to store a new one, I looked linearly for an empty space in the array, and I stored something here, okay? Or here. Are they the same? So I jumped here 4 times, I jumped here 4 times. Why no?
Because we jumped directly to in the first one, we jumped directly to the position in the array. But the next one, we have to iterate to get to the last.
No. But
Then we have a pointer at the end of the linked list, so we just add it from the back.
no, I want you to think about it from a simpler way. I'm here. Okay. Let's say this is 0, this is 1, this is 2, this is 3, and this is 4. Okay. And then on the 5th one, on the 5th index, it's empty. Okay. I did the function, I did the generation of keys. I ended up going to the 1. I found it empty. Okay, there is 2 programmers. One programmer, let's say Riley, for example, decide I want to do it as a linked list. So if I have something usually that that it's taken, I'll install it as here as a linked list. Okay, and let's say we already have 1, 2, 3, 4 people, 4 values already stored here, and I want to get to the empty one, which is here. Let's say I'm searching. Sorry. Okay, so I want to get to the one here. This will take me 4 times. So I'm here 1, 2, 3, 4. Correct? To jump to this one, because I cannot go right away. I need to go there. I'm searching. Now, if I want to search another programmer, he wants to know. He wants to go. If I find an empty space, I'm going to jump to the empty space. I have 1, 2, 3, and then 4. Again, forget about the hash map. I'm just talking about from concept perspective. If you want to move 5 steps in an array or 5 steps in a linked list, is there a different? So far in the course that we've learned, let's talk about from this course perspective, from a time complexity.
For the array list, it's all one. The linked list.
No, you're traversing. You're searching for something in the array. You don't know the index. You're searching. Let's say. Talking about searching perspective.
The same.
Same so far that we've learned. Why? Because I need to jump 4 times here. I need to jump 4 times here. So it's all 4, for example. Okay, if I'm traversing. Okay, Riley.
If you were to like, they are kind of different because if you were to say you have a collision and you add to the bottom, Your hash table might be full, but your linked list, you could keep going forever, right?
Okay, that's another one to keep in mind. But what I want to tell you here is that sometimes when we're talking about the worst case, the time complexity for us here from calculating stuff, we may say, okay, this is the same thing. This is off and this is off and, right? Do you remember we said that's what we care about now? But at some applications, why don't we want to solve this by doing a linked list? Because let's say you're building something more like related to a compiler or operating system. Okay, and they care a lot about the time and like the smallest amount of time because you want to compile something. If you're going from a pointer to a pointer, from memory to a very long, very different address and a memory following pointers, this actually costs more than just storing something next to each other. From a computer science, from us, we don't care. But I'm telling you why, because I'm going to show you some slides and you're going to tell me, okay, we could have used a linked list, for example. I'm telling you, no, sometimes at some applications, you don't want to use this because you're jumping from pointer to pointer instead of just having something in the array. Yes, right.
But it's not an O of N time or adding, it's just
Now I'm explaining a concept.
small constant.
Exactly. I'm explaining a concept. We're not trying to solve the problem here. We're going to start solving the hashtag. I'm saying a concept. For example, when we said something that takes O of 2n and something that takes O of n, for us, does it matter? No. For us, we're going to say, oh, this is O of n, worst case linear. Do you remember when we said if you're working with robotics or whatever, engineering perspective, 2n, no, it's going to affect me. I want to keep it O of n. That's what I'm trying to remind you with this concept. Okay, guys? Okay. Now, anyway, let's now move. So again, so we talked about this. We said our problem here is that I want to have O of constant, and I can do that by having an array. And one of the solution is to reduce from 10 million, let's say, to 10,000. How can I do that? We talked about two things. Address generation, that means key generation. I need to figure out a new key. I'm not going to use the student ID. I'm not going to use the name. I need to have a new key. Especially why? What if your data doesn't have a unique key? What if you're just having a database of names? You don't even have a unique key anyway. Okay, for this case, yes.
Would there be a time, like the time at which you receive the name is kind of unique?
Exactly. So the same thing will happen with the student ID. If you take something that you didn't work on it from a function perspective that we're going to see, it's going to end up with creating an array that's so big and you don't need it that much. Okay, so that's the idea. Very good. The other problem that we said we will have is the collision resolution. And that's why we're saying hash tables are so good, but it's much more complex. If you remember, when we want to use an AVL tree, okay, I'm taking your student ID right away. I'm storing it, linked list, everything's working fine. I know I don't have to do all of this work, for example. But here, no, I have to do extra work. So let's take a look now at more concrete examples. So if I want to search for a key here, and I know that this is my table, is going to, because it's a table, that means it's going to be O of 1 if I know the index. Very good. Now, another thing, as we said, let's say you don't have a student number, you don't have what, and we're going to go with names. So we need to think about a strategy to generate this key, to transform whatever I have into an integer. Because if I want to work with indexes, I need to work with something that is integer so I can be able to access it. So for example, here, what did I say? I'm going to take the alphabets, the first letter of the name as a key. Okay, so cat is like A is 0, B is 1, C is 2. Okay, so if I want to store cat, it's going to be here at 2. Elephant for fox, whatever. So what's going to happen if I have another one like cricket? We said we're going to have a collision. So now we're just showing you what we were talking about in a more practical example. Now, I want you to keep this in mind. We're going to come back to it, which is the factor, the load factor. Keep it in mind. So that's how we calculate the load factor. It's the number of elements stored inside this array divided by the array size. What can I conclude from this? What is the loading factor? So for example, if I have it 0.7 or whatever, that means 70% is full. This array is 70% full. So something like that. We want to keep the load factor closer to 0. We're going to see why. So let's now talk about the first problem. Let's put the collision on the side. I want to talk about the address generation because this is my first problem, which I need to solve. I need to take any data to be able to do an address generation for it. You were going to see something called hash code and another one called compression map. What's the difference between them? The first thing I want to convert, let's say, cat into a number, and then also I need to be able to store all of them in a compressed array. Instead of 10 million, let's say 10,000. So usually it will look like this, but don't worry about all of these functions. We're going to try to give lots of examples. Now, something very important when you're building your hash map or hash code maps is that you need to give the same result. It needs to give the same result for the same key. So if I'm building a function, I cannot build a very random function. For example, Taha comes to me and his name is Taha, all of the information I put in the function, it gives him a key of 3. And then if I want to search for Taha, I put also the same information, it gives me like 7. It can't. Like the function that we need to choose need to be consistent. So this is something very important. And then the other things is, which is very important for me when I'm designing this, is a good spread. Why? Good spread in the array. Why it's important for me?
Because if you have like one index that has like 7 children and one index has 1 child and 7 children,
very good. So technically, if I put, let's say we're not using the linked list idea, we're going to put it on the side. Let's say I want to store all of them in the array, but if I have 5 numbers next to each other, and I want to add something or I want to search for something, if there is no empty spaces, it's going to cost me a lot to insert more stuff. We're going to see it more. Now, the compression maps, take that out of the hash, we're going to explain it. Okay, compression maps. How can I compress the map now? What do you mean by compress it? So the first one is the generation. The second one, how can I solve the 10 million and compress it into 10,000? One of the examples that I gave you is what? Is modulus. Usually there is many examples. One of them is division, which is modulus. And usually the best thing is to divide, to do the modulus with the prime. The other one, it's called MAD, multiply, add, and divide. That means I'm going to do multiply here and then add and then divide. So this is more complex. Why we want to do this? We're coming up with these functions to compress that will give me the best result. So let's take some examples. I decided I have an array of n, and I said, you know, the way I'm going to compress it, I'm going to do log n. So I want to be able to store here just 2 to the power of 9, but it's going to be based on bits. Binary bits, okay? 0 and 1, that's it. That's how I want to give my key. So this is just an example, guys. Again, if you go online, hash tables are so famous and so popular, mainly for what? Passwords, logins. How do you actually convert the password that you put? You know, when you want to do crypting, like, you know, cover these things, and you want to store it in a safe place. Okay, you're putting your password, but it's not stored as your password, or else it's going to be what? Easy to find what's your password. So it's encrypted using hash functions. It's transformed into something, and that's why the stronger hash function that you have, it's going to take much more effort for a hacker to be able to find what is this function that it's deciphering your password. So these are very fun. One of the assignments that we gave is actually how to do the passwords. It's actually very fun. So that's why you're going to find so many different functions online. For this course, we're going to use the modulus. For a given key, the hash code must return a sequence of bits, okay? Okay. Now, let's take an example. I want to convert instead of converting the alphabets of the names into just like 0, 1, 2, 3, because I'll end up, I want to convert them into 6 bits. Okay, just at 6 bits. This is an example. I can only take names with 6 characters. So for example, chat, I want to convert it into bits. So I'm going to take the C is this one, the H is this one, A, T, and then here for the last 2 empty spots, I'm going to always have this. Okay? Again, guys, this is an example, just for you to understand. If I want to generate something, a key, an address for a bat, the same thing. What is B is this one. Now, what happens usually? I said I want to store them as 9 bits. Okay, so I'm going to take 9 bits of these. That's why usually it's supposed to make it harder when you're hashing them. But they're going to be an issue. First of all, again, that's why we're spending so much time to design hash table. That's the disadvantage, but the advantage is of course. From where should I take the 9 bits? That's my first decision I have to make. Is it from the leftmost or from the rightmost? Yes, right.
Don't want the rightmost because the rightmost ones are always full. Not always empty, but most of the word will be empty, so it's not going to do much.
Very good. Do you see here? Riley is in a company and they were actually designing this. And they are thinking before writing the algorithm. Someone say, okay, you know what? We have multiple option, either the leftmost, the rightmost, or the center, for example. So instead of just trying them all, maybe we can just get rid of the options right away. So Riley thought about it right away from like this. But if I take the rightmost, sometimes, usually from the rightmost, I'll have the empty spots. Like if a name is less than 6 characters, I'll always end up with this 1, 0, 0, 0, 0, right? So that means here, if I'm taking the 9 bits, all the animals of 4 or less characters hash the same location. So what did Riley do here? He just eliminated an option without even coding, without doing anything so far. So I eliminated. That's how actually we go with the design step by step. Now we'll take, for example, the leftmost. What would be the problem in this case? You can tell me with the leftmost, choosing the leftmost.
It has like the two names with the same first 4 digits.
First 2 digits, because we were taking 9 digits. Very good. If I have anything that starts with CH is going to be the same now for the 9 bits. So that's another problem that I have. So someone will come up with a solution. You say, you know what? Maybe I'll take the most significant, least significant, and the central, and then I'll do an XOR on them. And then I'll store this XOR. Another person said, you know what? I can do multiplication or whatever. So that's how they start coming up with, everyone start coming up with his own hash function. That's why, again, you'll see many people have their own hash function. The most popular, not the most popular, it's one of the most popular ones is the modes. Okay, it's very simple and it's very good. We're going to use it in this course. So we're going to see lots of examples on this. Now, the other problem that we're going to move to is what is collisions. So I solved the first problem. I have Fida came here. I did an address generation for her. No, the first thing is I did my size. I reduced my size. I did the hash map, and then I generated a key. And now I need to start worrying about the collisions, because many people are still believing, okay, but what about the collisions? Because we're not going to use the linked list, right? We want to actually store everything in the array, so I'll be able to go off constant. I don't want to come here at index 2 and then have a linked list that I have to traverse. I want to try as much as I can to keep it off constant. Okay, guys? So in this case, this solution, we said, what's the problem with this solution, creating a linked list here? It's not going to be good for me. If I have C here, it will end up with linked list. I have to traverse. So in this case, it's not good solution to use linked list or remove or enter. I want to think about something better. So I'll take Coyote. I said C is occupied at 2, so I have a collision. Who can give me a solution now to store it inside the array and still have O of 1? Abid.
Can we use the same hash function to generate an empty index? For example, the next empty index.
Yes, yes. So technically now we didn't use the hash function. We're introducing the steps to use the hash function. But one of the functions can be what? The next index. How can you achieve this next index using this function? So for example, can you look at this and come up with a simple function that will work? Not a mathematical function, just like the idea, and then. So you arrived at 2, it's occupied. What would you do? Multiply by 3.
I think I might have misunderstood, but like maybe you could do it in alphabetical order. That's what I was thinking.
So here, this one, look, so that's the different guy. This is an empty, this one here. That's an empty array that you created with the hash map. So you created an empty array of whatever number, size. Now you said, I'm going to use, for example, the first letter as my index, my key. This is not good example, but we're learning from it. I said we're going to use that. So initially, it's going to work out for you. Cat is here at 2. Elephant is at 4. Forget about the cricket now. 5 is fox. So that's initially it's working out for you. But now you have a coyote. What's going to happen? You're going to go to 2. It's occupied. So what you should do?
Yeah, I have to be create another index or
It would be with like, it would consider O instead of C, for example.
Like you move to the other one. Okay. Yeah, all of these are solution usually, but we want to take the most efficient one. Let me see here.
I do like plus 26.
Plus 26.
The next set of alphabet.
Okay. But we want to get rid of the idea of having a linked list or anything. We want to only have this array. So whenever I store it here, if I know the index, it's going to cost me off 1. So that's the idea, kind of like. We don't want to add any other data structure on top of it. So as simple. So Abed said something good, like I'm going to go to 6, but the problem in what he said is how he calculated the 6. He said 2 times 3, but why? Why? How did you get 2 times?
It depends on how many elements we have and
I want simpler than that, guys. Simpler, much simpler. Like look at it, and I want to move. So I have the cricket, I have cat, I have cricket, I have element, I have fox. So I want to move. How can I move? Very simple. Yes, right.
So if you go to cat and it's full, add 1 to your hash, like.
Yeah, increase it by 1 linearly.
If you do that, you're gonna have to check and see if it's full, but then then because you're going through and you're.
Yeah. So now you're coming to the end of the slowly. So guys, I'm here at 2. It's taken. I go to 3, it's taken. 4, taken. I'll store it at 6. So I'm going what? Linear probing. That's called linear probing. Okay. Again, what did we say about hash tables? So good if we build them or design them in the correct way. That's why the better hash function that you're having, the better probing function is going to work better. We're going to see if you're not using linear probing, if you're using quadratic probing, it's not going to, you don't have to traverse as much. And then we're going to see something called double hashing. If you're using double hashing, you're not going to do, you'll be doing this. Okay? So don't burn the story, right? We're going to end up with what you want, not now. So you get the idea here. So that's the first thing. That's called linear probing. So linear probing has this scary function. If you look at it, it's scary, but technically I did slides for you that it's very simple and it should work fine. The idea here is that have all of these keys, and because we're doing the plus one, right? The way we're going to do it is that the first one is H0, H1, so we're going to add here. We're going to see it in a better way. This is the algorithm for it. So let's go to the actual linear probe. So this is the performance, this is the average number of probes. You remember when we said here, but there is a problem, right? If I'm using linear probing, I will end up maybe going towards the O of n, correct? So this is how I know what is the average number of probes for linear probing, the average number. It's based on what? It's based on the load factor that I calculate usually. And then it's going to give me this. So if I put the load factor here, I'll be able to know that if my load factor is 90%, that means if 90% of my array, let's say this class represents an array, and it can fit 140 students. I have 120 students already in this. What's going to happen for me? My average number of probes, it will increase a lot. It's going to be 5.5. That means my chance to end up with O of n is very high. What can we conclude from this? If I'm designing this and I don't want to end up with O of n. Yes, Riley.
We want to have only 10% full?
It's not practical, but exactly, we want lower. We want to keep this loading factor. That's why I told you the loading factor is very important. I want to keep my loading factor less, okay, low, to be able to end up with a better thing. Now, this is not practical because now, for example, Riley say, oh, well, we can keep it just 10%. It's going to be good. Why would I create an array and reserve memory and then only use 10%? It's not good. That's why we're going to introduce something that's better. That even with 90% is going to be, for example, 2 point something. Okay? So this means that the average probing number of probes, that means it will take me averagely 5.5, let's say 6 probes each time I want to find something, if my array is 90% full. But if I built it in a better way, it will only take me on average 2 probes to be able to find my number. Do you see the idea now? That means at some point, if I'm designing everything properly, I'll end up something closer to O of constant all the times, even if I have 90% full. So that's the idea. But now I think the conclusion is almost done here. What is the worst case? Because we've burned it now. What is the worst case?
O of n.
O of n. You see, worst case wise, it's O of n. So everything that we're designing, guys, will always have advantages and disadvantages. You're using an AVL tree, you know for sure that the worst case will never be more than log of n. Okay? But it's very rare to be able to have O of 1 with an AVL. But here, with the hash table, okay, you know that the worst case scenario will be O of n, but in average, if you designed it very well, the hash table, and expected of 1 if you designed it very well. Okay? So advantage and disadvantage of stuff depends on your application, on the number of data, what are you trying to build, all of these kind of things. So here I'm summarizing the steps for you to do the linear probing. So we're going to do linear probing today, and then next week we're going to do the quadratic problem, double hashing, and we're going to solve from past final and midterms exercises together. So 2 things to solve any example. I'll need a hash function and I will need a collision resolution. These are 2 different things, guys. The hash function that I'm choosing for the next example is this one. Do you remember when we said we can have the binary things, we can have XOR, we can have the MAD, multiply, add, and divide, or we can just have this one, the mode. So this is my hash function. That means this is the first thing that I'm going to try to generate an address for Fida when she enters this class. Now, if Fida finds its place, I'm not going to jump to the second one. That's very good. I'm done. The hash function worked. Now, if she found that no, there's no empty space here, I need to go and use my collision resolution. Okay, my collision resolution for this example is the linear probing. So I'll be using this one as a collision resolution. So let's see an example. The size of the hash table is n equals 13. That means if someone enters, let's say someone with a student ID 13 enters, how can I calculate its address generation in the beginning? Sorry, before that, because I want O of constant, that means if I have the hash table is n equals 13, that means I booked already in the memory 13 memory chunks using indexes. So I'll be able to access them right away. So what am I going to do, guys? I'm not going to look at the linear probing function first. I'm going to go right away, key mod n. So 13 mod 13 is 0. So where I'm going to store it? 0. Good? Very good. I want to do 15. 15 mod 13 is 2. Okay, fine. 15 is going here now. Now, if I want to search for 15, I'll do 15 mod 13. It's going to take me to 2. So I'm able to what? Access it off constant. I didn't have to go through 0, 1, 2 to find it. You see why it's a powerful tool? Okay. So imagine you having 10,000 value, 1 million value. Imagine you have 1 million and you're taking off constant to go there. It's actually a very powerful tool, the hash table. Now I want to do the 5. 5 is going to be 5, and then 28. 28 mod 13 is 2. 2 is what, guys? Occupied. So now I need to go to the next step. What is my next step? I need to call the linear probing function. So first, this function here, this HK, is the first one that you always calculate. So that's 2. Okay? So guys, I made all of these colors for you because through the semesters, I noticed there is lots of confusion when it comes to this. So please follow the color when you're studying. Actually, it means something, the colors that I'm putting. So look at these. First, we said if I'm having a problem, I'll do these what? I'll end up with H0, H1, H2, H3. Okay, I have to follow this now. These are each H is the first probe, second probe, third probe, okay? So now, my H0 is my first probe, right? Which is, I already tried it here. That's H28, that's 2. That's my first probe. Now I want to go to the second probe. The second probe will start with H1, not 2, because we start H0, H1. That means I'm going to put H28, that's H28 here, plus what here, the J, the 1. Okay, so that means 2 plus 1 mod 13, that's 3. I solved it. That's 3. Clear? Okay, let's look at it again. Look at the colors. HK, I got 2. 2 is occupied, correct? 2 is occupied. Then now I have to use the H0, H1, H2, H3. I have to use the linear probing. So my H0 is the first one that I did, which I ended up with 2. Correct? Even if you want to use this, what is plus what here? Plus 0. So it's going to be the same as this one. Is this clear? Very good. That's 2. That's my first probe. Now I move to H1. I'll always have the H28 plus the J, which is here. J is based on this one here, the 1 plus 1. So that's 2 plus 1, 3. That I end up with 3. Yes, right.
Why are you doing your +1 inside of the mod and not outside of the mod?
That's how they did the function.
Okay, so it doesn't really matter. It's just that's because we're doing it because we're doing it.
Yes. Yeah. So that's not because we're doing it because that's a mathematical function. We're not going to prove the math behind it, but that's how it was designed. That's the linear problem. So if, for example, this H1, I also got like 5, for example, I need to go now with what? H2. If I go with H2, guys, how can I do H2? The touch screen, H2. Okay. How can I do it? No, that's the thing. It will always be H0. So that's usually the confusion, but very good. So that's why I wanted to ask. So it's going always to be H0, the original one. Okay, guys, that's why I asked. So it will be 2.
And then for J, I think with J is gonna be like,
2, because H2.
Yeah.
Exactly, and then you do it. Okay, we're going to see an example of that. So now, what is the, we covered this, correct? I don't want to cover the quadratic today, but I want to show you something. Let's say we're doing this. I want now, I inserted everything, and I want to find them. I want to find 14, so it took me 14 mod 13 is equal to 1. Where did I go? I go here. Is this 14? No. I need to do another probe, using linear or quadratic. We didn't see the quadratic, but here, this example is using quadratic. So probe 1, probe 2, probe 5, and then probe 10, we found it. I found 14. Okay, guys, look at what's going to happen now. I want to delete 5. Okay, so I do 5 mod 13. This is very, very, very important, this. 5 mod 13. I deleted 5. Okay? Now there is a problem. Why? I want to find 14. Do you remember when we said if you want to find 14, you have to do probe 1? Okay, it's not here. 1 is different than 14. Then probe 2, 15 is different than 14, sorry. Probe 5 is different than 14, and you continue till 10. Now I don't have this. So if I come here and I check it's empty, I'm not going to continue. Did you get the problem? This is a design issue. And if you write your program this way, the whole hashtag is not going to work anymore. How can we solve this? First, we didn't understand the problem, so I can repeat the problem. Then we're going to answer how to solve it, and then we're done for today. Did you all get the problem? Okay. Who can think out loud? You don't have to have the solution. What is one of the solutions that we can do? So Anthony.
Can you repeat the problem, please? I didn't understand.
I have this here. Usually, to be able to find 14 using a function. Let's say we have the function. So we tried the function, we tried the normal one. It showed us here. So we're trying the collision resolution. It took us here to 2. It's also occupied. And then we tried it again. It took us to 5. It's also occupied. So we continue doing it. It took us to 10. We check, yes, 14 is equal to 14. So I found it. Now I'm saying, okay, I'm deleting 5. I deleted 5. So this is empty. Now, if I'm doing probe 1, that means I'm doing the calculations, the function here. That's what I mean. I'm doing this function. It showed me 2, right? It's occupied. I'm doing it again. It's showing me 5. Now, when I go to the 5, to the index 5, I went to this index 5. It's empty. And usually, if it's empty, that means there's no 14. So how can I solve this problem after deleting something from the array? Because originally, when we inserted 14, there was a 5. So we came to the 5 and said, okay, it's occupied. Let me go to the further one. But now we deleted 5. Searching for 14. I want someone new. How can we solve this issue, guys?
Every time you delete something, you check the next one to see if there's a variable.
It's costly. It will cost me. Anyone from this side? Yes.
You can try to insert like a placeholder value or just kind of a.
As simple as that. Do you see? Very simple. By the way, this trick, usually as a programmer, you're going to always use it. Do you remember when we used to say, okay, we'll put a flag? When we were creating a linked list, what did we do? How are we tracking the tail? Do you remember in the linked list? We said we always know the head because it's the first one. And you always ask, okay, why do we also have access to the tail? Because when you're creating it, each time you're adding, you're saying, okay, I have this flag that I'm increasing the size of it. So I'm keeping a track of something. So always putting a placeholder or something or a flag, it's useful. So in this case here, what's going to happen, I delete something, I put like something like a placeholder called available. That means if I'm checking here, I'm not going to find null. I'm going to find available. That means, okay, keep searching.
So how do you choose the right kind of, like, it can't be a number because you're using numbers, right? So how do you know what you're supposed to do for the flag?
There is the, you can check the Java code for this, but you're not going to choose a number. You can choose a Boolean, you can choose like, that's why we put this available here, like as if it's like a Boolean thing.
So you could literally just put true or something.
Yeah. We put available because, again, from a design perspective, you're learning introduction to software engineering, I'm assuming, you always need to do the names properly. So if someone is reading this, because let's say you're building this code and you put true, no one is going to understand this.
Just anything but a number.
Yeah, yes?
To find 14, why do we jump from 2 to 5?
Because this example is for the quadratic problem. We're going to check it. We did the quadratic problem, not the linear one. We don't add plus j, we add here plus j squared, but I don't want to go through it now. So we're going to go through this exact one again, but I just want you to grasp the idea of the available because I skipped it here on purpose. So if you go back to this slide here, look here, it's already talking about this. To handle insertions and deletion, we introduced a special object called available, which replaces deleted element. But I skipped it on purpose so we can ask you about this. Yes.
How far is the here is first one?
Yeah, that's what I was telling. So this is using a different equation. We're going to learn it. Yeah. No, a cost of one expected in general, when we're done from this hash table, if you do it right in a very good way, you're going to end up with O of constant. Okay, so look what happened. Look, guys. So the reason why we teach you this, so we talked about the linear probing. We said this is not good enough for me. Why? Because look, if the it's 90% full, it's going to cost me 5.5, correct? But look, when I teach you about the quadratic probing, you're going to end up with, and we're going to see it in the next lecture. Look, 2.7. It went from almost 6 probings. So the average of how many times you're going to jump to find something, it went from 6 times to 3, for example. Now, if you do the double hashing, which is this one, this is a bit more complicated. You're going to end up with still 2.5. That's when you're going to say, okay, this is maybe my limit, or I have to come up with something better. And then at the end, we're going to conclude is the worst case is going to be O of n for sure. But the expected running time, what do we mean by expected? That means I hired a very, very smart graduate of computer science or software engineer. He's very super smart. And I'm expecting to him, if he's designing a hash table, he's going to do his research, he's going to design it in a very well way. That means I'm expecting to be of 1 if I design it very well. Now, and from this course perspective, in the exam, what is the worst case of hash table? Of n. Okay? And that's it for today, guys. We'll see you next week.